So we need to start this discussion off with what exactly is a log, which is short for logarithm. Okay, so it's written as such: log base b of a equals x. Okay, so what does this mean? What a log is basically it asks the question, what exponent do I have to raise b to in order to get a? This is saying that a equals b to the x. Okay? The log asks, what exponent do I need to raise b to get a, and x is the answer. X is the exponent that I need. Forward that into some of the more intuitive log rules with reference to our exponent rules. If you haven't already watched the exponents video, I suggest you go do that because it's useful to be able to understand this in the context of exponents. Anyway, if I write log base b of 1, what does that equal? Let's break it down. It's asking me, what exponent do I need to raise b to in order to get 1? Well, we know that there's only one way to get 1, and it's if I raise b to the 0 power. So that's one log rule. It's pretty intuitive, but it's one we gotta remember. Now, another log rule states that if I have log base b of b, that asks me, what exponent do I need to raise b to in order to get b? That is the exponent identity. If I raise b to the 1, I get b. So that's this identity. Next, we're going to move on to some of the more complex rules. That is, if I have log base b of some number m times some number n, then that is equal to log base b of m plus log base b of n. Next one we have is if I have log base b of m divided by n, then that is going to equal log base b of m minus log base b of n. Another one is if I have log base b of m raised to the n power, then that is going to equal n multiplied by log base b of m. Now, very important thing to recognize here is that this is log base b of m to the nth power. This is not equal to log base b of m all to the n. That's a squared. I meant to say all to the n. Okay? These are not the same thing. It matters where you put your parentheses. Okay? Now, the final one is the very important one that you're going to be using to solve a lot of your logarithm-based equations, is if I have a function, let's say the function y equals log base b of x, okay? What I can do is I can have b raised to both sides of the equation. Now, let me write that out for all of us. When I say raise b to both sides, I mean b to the y equals b to the log base b of x. Okay, we know that what I do to one side, I have to do to the other, and this holds true in that case. But an important thing to know in this case is b raised to the log base b of x equals x. Therefore, this equation can be rewritten as b to the y equals x. So basically what the logarithm is doing is in the same sense that multiplication is the inverse of division, and addition is the inverse of subtraction, and square root is the inverse of square, log base b is the inverse of raising something to the b. And so now I can take this equation and I can go right back. If I take log base b of b to the y, that gives me y, and I need to take log base b of both sides now, log base b of x, which returns me exactly back to what I started with. So now let's do some practice with logarithms. Let's say I've got log base 2 of x plus 3 equals 4 plus log base 2 of x minus 3. Okay? So I've got a bunch of messy logs here that are both raised or both with reference to the same base. So I can take 2 and raise it to both sides, and I should have something I can work with. Equals 2 raised to the 4 plus log base 2 of x minus 3. Okay? Now, on my left side, these cancel out, and I'm left with x plus 3, but I have a pretty messy expression here in my exponent on the right side. But we should remember from our exponent rules that when there is addition present in our exponent, that can be split back into multiplication. What I mean is, this is equal to 2 to the 4 multiplied by 2 to the log base 2 of x minus 3. And now, this is much simpler to work with. So we're left with x plus 3 equals 2 to the 4 is 16 times, these cancel, x minus 3. X plus 3 equals 16x minus 48. If I subtract x from both sides, I get 3 equals 15x minus 48. And if I add 48 to both sides, I get 51 equals 15x. Which therefore results in x being equal to 51 over 15. Okay, and if we want to simplify this a bit further, that is also equal to 17 over 5. Now we're going to try one more example that I think is the hardest out of the bunch. We have log base b of x squared equals log base b of x all squared. Okay? So remember my log rule, I can take this squared and I can bring it out in front of the log, and that leaves me with 2 log base b of x equals log base b of x squared. So what I want to do at this point is I kind of want to get all my logs to one side. So if I subtract 2 log x from both sides, I get 0 equals log base b of x squared minus the 2 log base b that I subtracted. Okay? So here, now I'm going to bring in my factoring knowledge. I'm going to factor out a log base b from both sides. Okay? Log base b of x squared divided by log base b just leaves me with my original log base b of x minus 2 times log base b. That remains just as 2. Okay? These, remember, equal 0. So in order to make this a true statement, I need to get either this guy equal to 0, or I need to get this guy equal to 0. Okay? So now I need to ask myself, what can I do to log base b of x to make it equal 0? So recall that this is what power do I need to raise b to get x? Okay? Meaning b to the 0 has to equal x. So b to the 0 is 1, at x equals 1 is my first solution right here. Then I can consider this part. So log base b of x minus 2 has to equal 0, okay? Or log base b of x has to equal 2. I get b to the log base b of x equals b squared, such that x equals b squared, whatever b might be. So these are going to be my two solutions to the equation. So now let's look at the general representation of the functions of the logarithm. So the logarithm is shaped generally like this, okay? Where it continues to get flatter and flatter and flatter, but it also continues getting higher and higher and higher to infinity. It's a weird function like that. But regardless, you'll notice that if this is y equals log base 10 of x, you'll notice that I have an asymptote here at x equals 0. It's because I'm never able to plug in 0 for x. If I plug in that, what do I get? I get, what power do I need to raise 10 to get 0? There does not exist such a thing in the world. So this is undefined. Also, we'll notice that we have an x-intercept right here. That occurs when log base 10 of x equals 0. What power do I need to raise 10 to get 0? That occurs when x equals 1. So, some understanding of the logarithmic function. Thank you guys for tuning in. Again, if you ever need extra help, join the Discord server.